If you're a chemistry teacher in high school tuning in today, you will totally be able to relate, I think, when I suggest that our lecturing to students and leading them in our classrooms isn't really the only thing we rely upon or expect from students is to do some notes. Instead, we're also requiring them to do some rote memorization. They're just things they have to know. And also repeated practice, because there are things they have to do. And chemistry especially, much like math, sometimes you just don't get in the groove unless you do it again, right? And if you're another secondary science teacher tuning in, you might be feeling the same. You might be like, hey, I'm over here not teaching chemistry, but feeling the same thing. Feeling like I'm resorting to the same approach with my students. Well, truth bomb, rote memorization and repeated practice. Neither of them are going to equip our students with the reasoning skills they need to support any claim in any science class or any life situation anywhere. Because the truth is, reasoning comes from evidence. Reasoning comes from experience, and in courses that are a little bit more challenging, a little bit more abstract, a little bit more complex, like chemistry, or maybe whatever it is that you teach, it can come from modeling. So in this video, I'm going to share with you my complete planned lesson for teaching the octet rule without rote memorization and without repeated practice, but with lots of evidence so that students come away with reasoning. And also, I'm going to probably plant the seed with you that I believe I can make an argument for all 7 of the NGSS cross-cutting concepts showing up in the activities students need to do in this planned lesson to understand the octet rule. Now, I do sell this lesson in my Teachers Pay Teacher store, and it's also available as part of my year-long curriculum I call Micro to Macro, a curriculum filled with nearly everyday active learning like you're going to see in this lesson. All the links to all of those resources are down below, and if you are not a chemistry teacher, you couldn't possibly use this lesson yourself, well, stay tuned, because I think you're really going to learn a lot about student-centered, inquiry-based lesson planning and really putting the onus on the students to dig and to do science, to come out with their own learning, and in so doing, build their confidence. If we haven't met yet, I'm Lisa, and I'm the creator of Lab in Every Lesson. And I believe that as science teachers, we have a huge responsibility to our students to impart so much more than a textbook full of content knowledge. I believe that if we show up every day with the intent for our students to investigate, for our students to dig out those core ideas we need them to know, and to sort out how to accomplish those skills we need them to do, then we're imparting them with life skills that go far beyond graduation in high school or even just simply leaving your classroom at the end of the year. I like to believe that I'm giving them tools for making decisions and aligning observations of the world around them so that they can come away with a better understanding. I have just 1 year with them, and so my whole approach is to condition them for something larger than whatever it is I'm teaching. I hope you'll join me. I'm so glad that you're here. Now, before we dig into the specifics of the octet rule lesson, I'm really quickly showing you this spreadsheet, which is an entire scope and sequence, I suppose you would call it, for what I refer to as an all about electrons kind of unit in chemistry. All of the lessons that you see here address the NGSS standard strand, structure and properties of matter, and specifically that standard that reads, using the periodic table as a model to predict the relative properties of elements based on the patterns of electrons in the outermost energy level of atoms. Now, if you're watching as a chemistry teacher, you and I know there's a lot to unpack there. And if you're teaching according to like a textbook outline, you might feel a little bit of like, wow, that encompasses so much. But it really drills down for me to about 8 lessons, may or may not be 8 days this year for me teaching it, absolutely not 8 days. But maybe if you work with some advanced students or in an honors class, you can accomplish it in 8 days. What I want you to know right now in looking at this is, firstly, you can download it. The link is in the description below. You can have it. It includes all the science practices. I believe each lesson includes, as well as the cross-cutting concepts, links to all of them in my Teacher Pay Teacher store, and even the learning intentions and success criteria that each of them is targeting, so that you know exactly what we're going after in each area, in each lesson. But really right now, I just want to prepare you with required prior knowledge, because when you are teaching in an inquiry-based design, hopefully it is not just an inquiry-based design for a single lesson, because the more consistent we can be with our students in bringing them interactive learning opportunities, the more conditioned they will get to do that, the more practice they will have in the art of investigating life. And so I want you to realize there's so much prior knowledge students should have leading up to this octet rule lesson. In my classroom, when I deliver this, I am teaching them first the Bohr model of the atom, which sets the stage for the circles around the nucleus and the fact that electrons move, not in pretty little circles, not in actual orbits, but that they jump and fall away and back toward the nucleus. Then we are embarking upon an atomic radius discussion, because it's a natural segue. When we explore the fact that there are these orbitals surrounding a nucleus and the sheer number of them, that impacts size. And it's the number one impact to size. And then pulling in that pattern of the periodic table, using the periodic table as a model to see the trend. And this is a trend that we're going to be able to use later on when we're talking about maybe ionization energy and the impact of size on the energy it takes to pluck an electron from that outermost orbital. From the Bohr model and basic atomic radius, we're going to Schrodinger's model of the atom, orbital diagrams and electron configurations, because he was pretty significant in our understanding of the modern day model, and really continues to play on that idea of energy level. And as per the standard, calling out the outermost energy level of atoms, really important for students. Oh, and also, if you're working in the NGSS and developing and using models, such a key component to especially chemistry, because we're studying everything we can't see, to explore those models, and not just explore them, but stack them so students can read and write all of them as a matter of disciplinary literacy. Following that with what I call fondly here shortcut electron configurations, but are actually electron configurations mapped to the periodic table. So again, back to that periodic table as a model, where the way I see it, every single one of these models allows students to predict properties and patterns of electrons, if we are teaching them to dig for evidence and sort out the reasoning. And then after all of that comes the octet rule. So I hope you will see, as we're looking through this, my students would really need to know that first. I would never want you to jump into a lesson or feel like, this sounds like she really must know what she's talking about. I'll use her lesson, and then you open it and you're like, they can't do this yet, okay? But also I want you to realize how much one lesson plays into another, and how that discovery and whatever we're focusing on in terms of the science practice or the cross-cutting concept might also play a huge role there. Now, I usually also will talk about the cross-cutting concepts involved in the lesson when I do these videos, but because I really feel like this lesson touches on all 7, I'm just going to forego that. Also, my videos here tend to be a little bit long, so I'm hoping this will cut down on the time, because I know your time is super precious. All right, one last thing I promise before we jump specifically into this lesson. Every single one of my lessons, if you've watched any videos here on my channel, you know that they've got 5 parts. In so much as I am able to accomplish that in one period, again, I have found it really depends on the group of students you're working with. If they are pretty astute, pretty engaged, you're going to get through this in one lesson, maybe even faster, and provide some extension. Maybe then throw them that repetitive practice. when you're working with my student, which by the way, I work for an online cyber school, lots of at-risk students, lots of 40% special ed, it's a different ball game, and I have to really put the brakes on. And in so much as I don't want to go there yet, but time is of the essence here, and I don't mean that in a sense where like you need to rush. You don't need to rush. Quite the opposite. If this is your first time launching into a student exploration on a concept, on a core idea, not in a conventional wet lab activity, then you want to just take it easy. Take it slow. Let students lead. Let students set the pace. Okay, back to my 5 pieces. I've got 5 pieces to my lesson planning framework. What you're going to see here is a review preview warm-up, super intentional, intended to activate and integrate prior knowledge. All that former stuff I told you the students need to know and do, it gets tied in the beginning. Then I give them some really nice clear objectives in the form of learning intentions and success criteria. This way they know why we're learning what we're learning and how we're going to go about doing it. The why we're learning what we're learning, because it's a single standard we're going after, it's pretty repetitive. Pretty much every day we're trying to get to the reasoning for bonding, the reasoning for chemical change. But every day, and the success criteria looks very different. And it contains a mix of, I am successful when I've done these things during class, which is ensuring students can measure their own engagement level in your class, and that you can measure it too. And then, of course, assessment-specific success criteria that lets everybody feel good about how the test might go, or how the quiz might go, or how that homework's going to happen. And really intended to use and to provide for students as a measure of their own progress, always. After clear objectives, we're pushing them right into an activity. And that activity should be designed in a way, or when I'm designing it, is designed in a way where students are going to dig, they're going to investigate, but the primary onus is on observing, collecting what they see. And my job is to organize an artifact such that they are then able to analyze those observations to come out with a big idea or some more questions, just as a scientist would. My students, they don't have that skill yet to collect the information. And honestly, most of our high school students don't. That's where our expertise is really going to shine. We walk them through some data-dependent analysis, some really pulling out the guts of the core idea, and then finish off with some skill practice. That repetitive rote practice that now they have all the reasoning for and all the tools in their toolbox to sort through and think through and explain through, making it perfect opportunities, so many perfect opportunities to give them claim evidence, reasoning scenarios, rather than just a whole bunch of standardized test questions. Okay, without further ado, the review and preview for this octet rule lesson is a series of 5 atoms that I've provided them with a periodic table in the corner. The periodic table is not super legible. I mean, in terms of, you could not sort out probably the atomic masses, but certainly the atomic numbers. It's there because, remember, this standard has them using a periodic table as a model and always going there to see what we can learn from. The important part of this table that I like to embed on the same page is the group A designations, because I find it really hard to find periodic tables online with that. I've really actually only been successful finding one link. Many of the others just number in the teens, and as of course of you and I know, especially for the octet rule lesson, they are not helpful to us at all. What I have students doing here is tying together all 3 of the models they have learned, because they are going to use them in their main activity of the day. So this is just a quick preview of the main activity that would come, which makes this activity extremely important to provide them. Because if you just go throwing at them the activity, here's a Bohr model, here's the electron configuration, here's our filled box diagrams, and now make changes to them, my students would be in complete overwhelm, complete and total. As it is, I gave them this preview very recently, and they still felt shock and awe. So, okay, great. So moving on. For each of 5 atoms, and I've tried to split it so we represent 2 metals and 2 nonmetals and a noble gas, because we're going into the octet rule, and we all know how important the noble gases are. What I want them to do is focus on the valence electrons in the Bohr diagram images. Show me that they know what the valence electrons are, because knowing your number of valence electrons, of course, is critical to being able to predict how any atom is going to chemically behave. Those outermost energy electrons, those highest energy electrons. And then I want them to take the completed Bohr diagram, which I've provided them, and practice filling in an orbital diagram from scratch, highlighting the valence electrons in that off-bow diagram. Now, students will usually just highlight the electrons in the 2p if we have 2p electrons, or in the 3p if we have 3p electrons. And of course, this is a challenge here and an opportunity I have to correct students that actually, and this is where stacking the models is so important, because what they will do is, let's take oxygen, for example, with 8 total electrons and 6 valence. They'll highlight the 6 valence in the Bohr model, and they'll only highlight the 4 in the 2p. And I'll say, but wait a minute, we have 6 valence electrons, not 4. Where do the other 2 come from? And so then we can really focus on the fact that the number of the energy level in the box diagrams in the electron configuration tells us the valence electrons. And it should match the group number on the periodic table, and it should match what we could draw ourselves as a Bohr diagram model, which is something I have them do in that Bohr diagram lesson. Finally, write the electron configuration. So here is, folks, a great example of some rote practice, but they're doing it where you are available. Maybe you're making this a collaboration opportunity. Maybe there's some divide and conquer going on among your students, different students doing different ones, and they get together and share their information. Either way, you're getting this level playing field where everybody knows what they need to know before they're going into that activity. Now, not included in the lesson that I sell is this slide where I go, pop quiz. I actually sat down this year and I said to myself, you have been intensely working with models and these students. This should be more than activate prior knowledge today, integrate prior knowledge. I'm going to count this. And I made this a 15-point assignment, pop quiz. And I felt real good about doing that. It was the first time in 4 years or something I did that. And the reason I'm sharing with you is because my lessons are so value-packed that if you ever feel the need to, in a pinch, or even because you're struggling to create one yourself, and you want to see what I have to offer, my lessons are so value-packed that you can often use various portions of them for different things. So I am not the curriculum resource seller out there who's also going to give you all your test items, because there's so much that lives in the lessons. And you're a professional, you know your students best and what would work. And case in point, sometimes year to year or class to class, you're not going to be able to treat each part of these lessons exactly the same as the one before it. I can give you the purpose and I can give you the reason it's designed this way, but the reality of our job is that we have to bend and flex to the circumstances and the situation we have, the cards we're dealt, right? And so sometimes that means this is an assessment instead of a warm-up. The clear expectations of this lesson, if you've tuned into my other lessons on the channel so far in this playlist, we're talking about learning the octet rules so we can have disciplinary literacy skills, practice using all of the terminology we've learned so far as far as valence orbitals and electron configurations, all the things, so that we can communicate, because communication's actually part of the scientific method and the scientific process. And the remaining here, too, they map directly to our standard in so much as we're using patterns observed among various models of the atom, and our goal is to predict chemical change. that will occur for stability to be achieved. We know that's the whole reason that atoms get together and bond, is because it's more favorable for them to be together than to be apart. And of course, the octet rule is the underlying theme for that. This is the reason really to study the entire unit, though, and ultimately explaining how my atoms undergo change through bonding, where bonding is my next unit in a curriculum. The success criteria is pretty narrow for this lesson. You'll see some of my lessons have, I don't know, 4, 5, 6 success criteria, depending on what I'm asking them to do. Defining terms in the word wall, I'm in the process of updating all my lessons to not read that, and instead to read accurately use these terms, because really I'm not actually asking them to define terms during class or even after class. I'm never asking a question on a test, what's the definition of an ion, for example? What's the definition of an isotope? What's the definition of an orbital? We don't do that. That's like super low level. If you're doing that, you need to ramp up the rigor in your chem class or in your science class. In this lesson, what you're going to see students do is just identify how many valence electrons are there in a model they're looking at, and then predict whether there's gain or loss that's necessary. Gain or loss that's going to happen for stability. Now, one thing I didn't mention in my 5-piece framework for lesson design is the inclusion of a mini lesson. Often, I can't say that's standard as part of my framework because it's not. Most of the time, my secret sauce is actually not telling students things. And like I said, intent to investigate, and they discover the core ideas. But there are lessons where they do need some background knowledge, and when they do, I just throw it at them as a word wall piece. I do present it as like, this is what it is. This is a noun, this is a definition. Where possible, I might provide them diagrams, maybe even examples, maybe even a model to look to as they do whatever they need to do. And the octet rule definitely is that situation, that lesson where I need to provide that extra support. So on this first page, I kind of go through this story with them about what is an octet. It's 8 electrons. And that's nature's decision. It wants 8. 8 is stable. 8 is great. But then I usually jump right to the noble gases. And here again, emphasizing the use of models. It's one of our science and engineering practices. And it's so helpful for us to get students to argue evidence. Okay, so showing here all the Bohr model diagrams, the condensed noble gas configurations for the elements, and noting that helium's an exception, but telling this story that by nature of the word noble, and I'll usually say to the students, what do you think noble means? And they'll come out with royalty or special or above all the rest or more important or very, very polished, things like this. I usually come right out and say, in American culture, we don't have royalty, but we have celebrities. And there will probably be a time in your life where you go to a hairdresser and say, give me Taylor Swift's bangs or whatever, right? Some people going so far as to inject themselves all up and get the cosmetic surgery to look exactly like the celebrities. And this human nature we have to want to look like the current trend or be like whatever Kim Kardashian is. Okay, not me, just saying, was never my era, never will be my era. And it's funny because when I tell the story, students they will chime in. I'm an individual, I am me, that's great. And we can have that little meaningful social moment. But they understand. They understand that, oh, these are perfect. And because that, they're not chemically reactive. For the purpose of high school chemistry, I do flat tell them they don't bond, they don't react. But everything else is going to want to be like them. All these elements, of course, we're not dealing with the transition metals, so I will go on to say this doesn't apply to any group B elements or certainly our inner transition metals. And then I say, here's the octet rule. Naturally, these elements will gain or lose electrons to satisfy this 8. They will want to look like the noble gases. And the looking like the noble gases is really part of that developing and using models to get this idea across. Now, if you're listening to me and you're a chem teacher and you're like, this lady, she is telling students the wrong thing because it's not just gain or lose, we can also share. Totally. I sprinkle that in. Sharing's possible, but that's a specific of bonding, and really I just want to simplify it for them. An atom's got to get 8. We're not going to entertain all the ways in which that's going to happen. Let's just focus on the issue at hand. Get 8. That means gain or lose. And so then I give them this activity. And I used to start with this slide. Okay, so this slide looks at period 2 elements: lithium, beryllium, oxygen, fluorine, neon. The same elements from review preview. So here we are, activated and integrating that warm up. Picking neon because it's a noble gas for comparison's sake. Picking lithium, beryllium because they're metals, oxygen, fluorine because they're nonmetals, and some clear instructions up above. I want them to make octets in the valence orbital, so I want them to draw in electrons if they have to draw them in. But if the electrons should get lost, cross them out in the Bohr model. And then do the same thing with the arrows in the box diagrams. And what this does is it's constantly tying together for the students that 2s and 2p is the 2 ring in the Bohr, 3s and 3p is the 3 ring in the Bohr model, and we'll cement that idea of valence electrons in time. I also asked them to adjust the electron configuration, and note with the octet, once it's been changed, once chemical changes happen, which noble gas model does it look like? And for all of these examples, not all of these examples, for 2 of these examples, it's going to look like neon. For lithium, beryllium, of course, they're the exceptions. They are going to look like helium. That's super challenging for my group. So I no longer start with this set. I usually go straight to period 3. And you'll see that in this example, I've also added the prompt boxes that read, will this atom gain 7 or lose 1? So I do also tell a little story here, and I'm getting away from myself a little bit. I wanted to talk about those 7 cross-cutting concepts, okay? So the pattern is going to come in the periodic table in time. And this idea of which elements will look like, this idea that elements will eventually look like or have the same total number of electrons as their closest element, the closest noble gas in atomic number. So patterns will come, but cause and effect is here, okay? The cause is I am unstable. I only have 1 valence electron. I only have 2 valence electrons. I only have 6 valence electrons. I need 8. What's the effect? A gain or a loss. So that cross-cutting concept is playing in students' head constantly throughout this activity. Also, proportion and quantity, scale, proportion, and quantity. We're looking at how many parts of the whole do we need? And actually becoming whole as it pertains to stability, which stability and change is also a cross-cutting concept in science. This very idea that every element will seek out this change to become stable. And it's something you do have to tell them is a truth. That's in the mini lesson leading up to why the octet rule. But it's something that they are applying in the doing. Structure and function is a big one here. Anytime we're using developing and using models as a main theme science practice, we are structure and function all day long. These elements react. That's the function. I mean, they don't know that yet, but the structure, the 1 valence electron leads to the reactivity function. The 2 valence electrons that are not 8 leads to the reactivity function. And then, of course, just working with systems and system models and the importance of every single electron to the whole. That's our 7 cross-cutting concepts here, in case you miss it. You have to really look. There's so much power packed in this lesson activity. Okay, back to the evaluation. So this is really scale, proportion, quantity, and also an energy piece, you know, because this is how I guide my students with this. I will say, listen, and you can see in the instructions here, it says, make 8 valence. To do that, you've got two options. Get rid of everything that's there, valence, or whatever the difference is to make 8. So if we've got 1, we've got to add 7, or we're going to lose the 1. If we've got 2, we're going to add 6 or lose the 2. If we've got 3, we're going to lose the 3 or add 5. Right? They understand those options. They don't have any basis for understanding why they would pick one or the other. So usually it's a matter of waving our hands a little bit, the energy and matter cross-cutting concept, because we're not quite there yet with ionization energy. That'll come down the line. And of course, it applies to all of them. We have some leading up to get to there. So what I will tell students very simply is, nature is lazy. And it wants to expend the least energy possible. Would you rather do 1 sit-up or 7 sit-ups? Would you rather take 1 test in a school day or 7 tests in a school day? So it really doesn't matter whether you're using the example of physical energy expended or mental energy expended. Teenagers don't want to expend any energy. So they quickly pick up on whatever is lesser as an option. I've laid out my options now. Look at the number of things. I want to do less. So that would prompt students to choose lose 1 electron, lose 2 electrons. Oh, oxygen, gain 2 electrons because it's only 2 things. I make sure to tell them these are separate events that happen. They're not just all 6 electrons come in at one time, or all 2 electrons come in at one time, or all 2 electrons get lost at one time. So they do need these clarifying pieces, which I believe will come up as your students work. And asking questions up on my wall here, not sure if you've ever noticed. These are prompts for me and my students. They're also rewards I give out. They are little badges that connect to science and engineering practices. And one of them is asking quality questions. That's part of science. So when they see things, sometimes they miss it. They think so fast. I want them to become aware of the questions that they're generating and to speak up, either to another student or to me, and it benefits the whole group, right? So you can give that to them as part of your mini lesson, mini lecture, or you could just wait until the question comes up. Either way, once they have made the choice, they can and will adjust the models. The part where we're getting to patterns, which is the ultimate call-out cross-cutting concept in the NGSS, and any state adaptation of the NGSS, like in Pennsylvania where we have steels, is to figure out and note this piece about the noble gas. That all these models and the total number of electrons at the end has to look like a noble gas, or the octet rule has not been accomplished. And so when you look at student work or when you reveal it, you're going to see here the pattern is that our metals, sodium, magnesium, they will look like neon, which physically on the periodic table is far away, but in atomic number is closer, 11, 12, closer to 10 than it is to 18. And our non-metals, so sulfur and chlorine with 16 and 17 electrons to start, are closer to the noble gas argon, 18 total electrons. And so that happens. So this might be trial 1. I do include in the lesson the period 2. Now, once we've been through period 3, I can confidently go to period 2 and say, do oxygen and fluorine and have a learning moment on the lithium and beryllium. Because at that point, they've done enough practice and we've seen the noble gas pattern emerge that you can, without telling them, get your students to know lithium, beryllium going to look like helium, even though helium doesn't have 8, and it kind of bucks the system. Okay, following up on all of that, I just plant the seed for my next lesson, which is about predicting ion charge. And this, again, sort of, it's a theme. All of these cross-cutting concepts, they extend from one lesson to another. We have just made an argument for the total number of electrons and the total number of valence electrons adjusting in that outermost orbital. Well, we've disrupted our normal state of concern, which is electrically neutral. What of that? And this is to come, cation, anion, ionization, and so on. As per value, there's some recommendations for adaptive practice you might consider assigning your students. Again, The rote practice, they decide they'll need. I do this activity called weekly practice in my course where students get to choose from a list that grows throughout the semester, and these two are on it. Of course, the octet rule and exceptions to the octet rule. So after the activity has been completed and we've talked through it, we've extracted that pattern, data-dependent analysis is closely connected to the design of your artifact outline. We're here and you're letting really the cross-cutting concepts lead. If you're watching this still and you're not teaching chemistry, the point you want to learn here today or see through the doing is that the design of the artifact you're going to have students work with, or where they're going to organize their observations, is going to be the thing that launches your conversations about analysis, about sorting it all out and thinking it through. And that's often happening aloud, whether in small groups with students and maybe prompts you were able to throw in ahead of time, or just simply class-wide discussion during the activity, as in the case, I think, of this lesson, because there's just so much to come up during that. Now, what we actually need our students to be able to do, again, is map this to the periodic table. The standard is all about using periodic table as a model for determining reactivity, predicting the relative properties of elements based on the patterns of electrons. So we're looking at the periodic table, and they should be able to, as a goal, and I think you'd agree if you're teaching chemistry out there, look at the periodic table and make the decision, is this atom going to gain or lose? If we're talking about ionization, of course, as we're heading toward ionic bonding. And just this basic idea, because honestly, it's very easy when you get to covalent bonding to just say, well, sharing is possible too, but 8 still is the goal. That's just waving your hands a little bit, no big deal on that. Starting out here with argon, how will a neutral atom of argon adjust? And that's just to set the stage again, remind them how critically important noble gases are and the part that they play. Of course, argon's noble gas and it won't do anything. And then there's a series of 5 questions included for you to go through with them, 6. So to predict, and really it's all of those period 2 and period 3 elements from the group A main group to reinforce that everything they did in the modeling are tools that they could use to problem solve if they need to, but what we've revealed is this pattern. And of course, what I do when I teach is to do the evidence and do the reasoning every time we answer a question or ask students to offer what they would share. And again, 2 patterns, and again, 2 patterns. If we align all we have learned and all we have sorted out in that class period, which elements are gaining and by how much, which elements are losing and by how much, and we annotate the periodic table, we can prompt this aha moment. All metal atoms are going to lose electrons. All non-metal atoms are going to gain electrons. It's only in my next lesson in the series where we're saying how many. How many are going to get gained? How many are going to get lost when we're predicting charge? Because that's too much for right now, but it sets us up for what's to come. There's also an exit ticket if you would ever purchase this lesson from me. Like I told you, value, value, value. And you get a digital notebook version where everything that I've just described is included as sort of a web page. You just have to share students a link. You don't need a special LMS or anything like that. You don't need a special subscription. Students can download a PDF when they're done. Interactive whiteboard, open fields, multiple choice. All the things I've shown you here are available there. Yeah, I get so excited. Do you notice? I get so excited by the end of these that I honestly usually don't know how to wrap them up. I'm going to say sayonara today and invite you to visit me again when I publish the video on ions and ion charges and predicting ion charges because my next unit is going to be all about the ionic bonding. Until then, folks, have a great day. Make today a great day. Usually we can't rely on it to just be good on its own. Thanks for joining me.